All right, so very similar to the disk method is the washer method. You would use the washer method when your rectangles do not actually touch the axis of revolution. As you can see here on the left, I have a big capital R for the bigger radius, and I told you that was coming. And now there's a smaller r for the smaller radius, and that's fairly straightforward. And basically, if I were to revolve it around this axis of revolution, and that's kind of what that little thing like that is for, that's what I always put on the axis of revolution so I don't forget where it is. Do you believe that this problem is way different than if the axis of revolution was right there? Is that a slightly different figure when you're done? Yeah. If I were to do just this rectangle over the red line I just made, would there be any holes in that? No. If I erase that red line and do it over the actual axis of revolution, there's a huge hole in it. Okay. So, and would you agree that the object that I just made there in red is much bigger than the one that if I would have done it over that red line? This one gets quite a bit bigger. Okay. And so that's where we run into a problem. And I look at it this way. Let's say this was kind of filled in right there. Well, wouldn't that just be, this is a circle on top, right? Which would just be pi r squared, right? And then we just have to take it by however wide it is. And isn't that basically disk method right there, if it was filled in? Okay. And so what we're going to do is we're going to try and figure out, well, what is that? And it basically, wouldn't that be a disk on the inside? That hole is basically a disk that I'm subtracting out, isn't it? And that's why that one would actually be pi r squared and then times w. Do you agree with that? So I would take this top one and I would subtract the bottom one, and that should give me the washer. Agreed? I'm taking the whole thing and subtracting out the whole. Or the entire thing and subtracting out the whole. So what did they do here? Well, what did they do with the pi in both cases in this problem if you look at the formula over here? Put it out front. Can you do that? If they both have a pi, can you factor it out and put it out front? Yeah. How come pi can go out front? Because it's just a number. If it was a function, can you throw it out front? No. But seeing it's just a number, you can't. Do you have to? No. If you want to leave pi in there, go right ahead. Now, the key here is, notice how big r is basically saying it's a function, because that's going to tell you how far it is from there to there, because that's what the big function is going to tell you, is that bigger radius. And notice what they're doing. They're having you square it. Why square it? It's pi r squared. Okay. And then over here they're saying subtract, and once again they're saying little r, because little r is that, well, you can't even see it. Let's do a different color. Little r is that much, correct? It's the radius of the hole, right? And so once again they are having you, though, square it. Okay. So where is w? It is the width. Where is it in that formula over there?
It's the b to a.
Nope. It kind of is. It's kind of the b to a along with this. It basically turns into the dx, is how wide it is. Because when we made the rectangles, didn't I always put a dx down here for how wide it was? Now, is x changing as we go from left to right in a lot of these problems? Yes, it is, but the function will take care of that for us. The key here, I would say to remember, is that the two functions, or the two radii, are squared separately. It's not like I subtract the two and then square. Big difference. You see how they are squared separately. And if you can keep that straight, this really isn't going to be that hard. Yes?
Two ways to find the volume of this washer percent?
There are several ways to find the volume of these washers, but what we want to do is find a method that basically allows me to put in as many washers as I possibly can into these graphs that we're going to look at, so that it'll find the actual volume of very strange looking objects, is the whole idea. And this is the quickest method for doing that. Obviously for this washer right here, could I figure this one out quite easily? Yes. But we're going to put a lot of these in, is the idea. And so the first thing I want you to graph is that right there. This is actually y equals the square root of x and y equals x squared. And we are revolving it about the x-axis. So get that graph in down there, and I like to put that in so I remember where I'm revolving it. And then I'm going to ask you which graph is x squared and which graph is the square root of x. I'm hoping you have enough knowledge to be able to tell me that.
Did we do like a pre-problem one of the previous notes?
We did a problem very similar to this on the previous notes, but our rectangles, I moved the axis of revolution in that other problem. Our graph was actually still touching the axis of revolution, where these rectangles will not be. Yes, we did one very similar on disk method. Yep. It was example 2, I believe, on day 1 of disk method, and that's because the rectangles were actually touching the axis of revolution, where these will not be. That's the big difference. So what do you think? The one on top or the one on the bottom? Which one is y equals the square root of x? The top. Very good. So this one here is y equals the square root of x, and so then the one on the bottom is y equals x squared. And what we're really going to do is we are going to put in, basically there are a bunch of rectangles going on here that would go across this. And so big R is the distance from the function all the way down. Does that change as we go from right to left? Does big R change? Yes. Does little r change as we move from left to right? Little r is that little bitty distance right down there. Does that change? Yes, it does. But us integrating allows us to say we're moving from left to right. That's the whole a to b thing. And dx says we're going to plug in a bunch of x values along the way. So that really takes care of width if you put those two together. So what I'm going to do is just show you what a couple of these discs, or actually washers, excuse me, would look like. So obviously the green one much bigger than the red one. Is big R different in both of those two washers? Yes. Yeah, is little r different? Yeah, a lot different. And we're going to allow that to change as we go from left to right by using integration. Because could I, if I wanted to right now, if I told you exactly where those were, you could find me the volume of those two quite easily. But I wanted to find the volume of all of them. What if I put 100 of those in there? What if I put 1,000,000 and actually find the volume? Okay. So if we actually took this, it would be a very strange object. It's the visualization of it. And it would be a very strange, almost look like a flower, I guess, if we actually revolved the entire area. Does everybody see that, what I'm talking about? And so what we're going to do is say, all right, well, let's figure this out. What I like to do before I even start is I try and figure out those two things. What is big R? Okay, so if I picked an x value, let's say I picked the x value of 1/2, that'd be right about here, right? You agree with that? What would tell me that distance from there to there? What would actually explain that to me? It'd be square root. It'd be whatever that y value is, right? And so the big R here actually is the square root of x. Because it happens to be the one that is, in this case, further. And it actually just happens to be the y value because I am revolving around the x-axis. Right? So whatever that y value is right there would tell me that. And how about little r? Little r is just that distance right there. What would tell me that distance? What would tell me that y value? Is putting that x value in where? X squared. Because x squared is this function right here. And to find that, it would be putting the x value in there would give me the y value that corresponds to that little distance I just put in green. Okay. So here we go. Volume equals. Why is there a pi involved again? Why is there a pi out front? It's a number, and it's pi r squared on both of these, right? It's the area of the circle, all right? Now, from where to where? Yep, 0 to 1, because that's where it's done, so 0 to 1. I like to use brackets. You definitely don't have to. And big R does have to come first because it should be the bigger value, right? And we're subtracting here. And what's big R? Oh, square root of x, but let's not forget. Again, why is it squared? Because it's pi r squared. It's the area of a circle, and then we are going to take it times the width, which for us is kind of like dx. Minus. So that's really big R right there. Minus whatever little r is, which is x squared, which we have to then also. It's very easy. You see how it would be very easy in that case to forget the square? Yes. Because there's already a square on it. But again, little r is just that portion. Again, the dx in the 0 to 1 kind of allows me to move left to right here and get all of them. Okay, how are we doing on time? No, we're doing all right. Well, let's do this one by hand. This isn't too bad. Now, based on what I've just written, do you believe I'm going to integrate in this step? Not yet, because I put the squiggle in there. What am I probably going to do? I'm going to clean it up. What's very nice about this one is this first big R here, when I square it, yeah, it kind of cancels and just leaves me with x, right? Minus, well, what happens with little r here when I square it? X to the 4. Okay. So again, I have not integrated yet. Now, it's been a while. So there's a pi here. Now what do you think? Am I probably going to integrate at this point? Yeah, I got that squiggle out of there. I probably am going to. And what do we got there? X. What's the antiderivative of that? X squared over 2, or 1/2 x squared. Either way is fine. Minus x to the 5th over 5. And now there is one more notation that could possibly help you remember that you actually took the antiderivative. And that's just basically, just put that line there and then put the numbers in so you don't forget. How come I did not put plus a constant on this one? Yeah, it's definite. We have our, that's a good way to say it. We have our window. We know from where to where. And again, there's a nice number in here, that 0 on the bottom. Zeros are normally going to be nice. And so here we go. We put, well, there's still a pi. Don't forget about that. You put 1 in. If you put 1 in this first one, we get 1/2 minus 1/5. Well, I better do it this way just so you don't get confused, because that's putting in the top number minus putting in the bottom number. If you put in the bottom number, you get 0, right? So minus 0. So you have 1/2 minus 1/5 minus 0 times pi. So in other words, this is, you probably got to go to tenths, right? This first one would be 5/10 minus 3/10 is 3/10 times pi, otherwise known as 3 pi over 10. Is your calculator going to give you that answer? Probably not. Your calculator would probably give you the decimal answer, which is approximately 0.94. Now, we don't know the label yet, but we do know if this was, say, inches, or if this was centimeters, we do know it would be centimeters cubed. Because basically, we would have taken the centimeters right here and squared it, and then take it times centimeters again. That's why it's centimeters cubed. Again, the true reason, not just because it's volume. Any questions on example 1?